Well, thanks everyone for being here. My name is Bryan Wilder. I'm a PhD student at Harvard University. And so today I'm going to talk about some recent work that we've done around learning optimization and fairness in social network interventions. And I'm actually going to start out with just a very brief picture of the kind of work that I do, and then I'll zoom into some of the recent work that I'm going to talk about. So at a high level, my work is about the process that we use to get from data to decisions, and how we can use that to improve resource allocation for services that impact vulnerable populations. So on the computational side, I study this kind of range of techniques around how we gather data, use it to do machine learning, use optimization to arrive at decisions. And then on the application side, I've worked on a number of projects around health services for vulnerable populations. And so this talk is going to be focused on one particular class of interventions, which are social network-based interventions. The idea here is that we're trying to disseminate information or change people's behavior via social influence. And this is often called influence maximization in the computer science literature, but it's a really widely used toolkit in health and development. So the particular project that inspires the work that I'm going to talk about is a project that we started several years ago in Los Angeles. And this is specifically, the health application here is HIV prevention for homeless youth. This is a really critical challenge because in Los Angeles, there's about 6,000 youth who are homeless at any given time. And those youth have about 10 times the HIV prevalence rate of the general population. So drop-in centers and shelters and other organizations that work with homeless youth will conduct educational interventions where they try to raise awareness about HIV and about prevention strategies. Due to resource constraints, though, these interventions have limited capacity. They can't deliver the preventative intervention directly to everyone in the population. Instead, they train a small number of youth as peer leaders. And the idea is that those peer leaders will talk to their friends, who will talk to their friends, and the message will diffuse outward through the social network. So the computational problem that we'd like to address here is how to select the most influential people to receive this intervention, right? Given a social network, who are the nodes that we should select given a limited budget that will have the greatest impact and influence? So over the last few years, we've been working together with social workers to develop algorithms that are suitable for influence maximization in this kind of field deployed setting in public health. So, and this primarily means being able to account for all the different uncertainties that you have when you actually use these algorithms in practice. You need to be able to efficiently gather information about what the social network structure is, find decisions that are robust on known parameters, and so on. And so we spent a while developing these algorithms and then deployed them in collaboration with Los Angeles area organizations. We've been running over the last 2 years a field study that just wrapped up that enrolled about 700 youth in total. And we find that the algorithmic approaches are really sort of impactful in this domain. That the blue bar here is looking at the sort of extent of behavioral change for youth who received an intervention planned by our algorithm, compared to the status quo approach in orange, which is just selecting the kind of most popular youth, the people with the highest degree in the social graph, and a control group that receives no information. And so here we find that using the algorithmic approach to plan the intervention results in really substantially higher behavioral change. And this has very direct implications for health. So this is great. We just got these results back recently. We're very excited about them. And the question is where do we go from here? And so today I'm going to be talking about 2 pieces of recent work that try to get at how we can deploy interventions like this, like social network-based interventions, in a way that's responsible and in a way that's scalable. So a program that we would really be proud to see scaled up to a much larger set of organizations. And so there's 2 particular sort of recent pieces of work that I'm going to be talking about. One is a paper that recently appeared at HCI about defining fairness in the influence maximization context. So making sure that our intervention isn't just good sort of in total across everyone, but that it's also doesn't unfairly sort of neglect subpopulations. And then the second piece of work is on the scalability side, thinking about how we can integrate together machine learning and optimization problems on graphs so that we can effectively do more with less data. So with that, I'll dive into the first part of the talk here, which is about fairness and influence maximization. So here, typically algorithms for influence maximization optimize total welfare, right? Defined as the expected number of people that are reached by the intervention. But this sort of neglects questions about how influence is distributed across the network. And in particular, you might worry that people in smaller or less well-connected groups would be less likely to get information than people who or in bigger or more well-connected groups. So the questions that we want to get at in this work are, do standard influence maximization algorithms neglect minority groups? And if so, if there are disparities, how can they be mitigated or avoided? So there's sort of this key set of contributions in the work. We first set out to kind of formalize ways of measuring fairness in the influence maximization context. We analyze the price of fairness, right? The sort of loss in utility that you may experience from enforcing any of these definitions of fairness. And then on the algorithmic side, we provide algorithms that can effectively solve the associated optimization problems. They can find sets of peer leaders that are fair according to whatever measure. And in the course of doing this, we actually make progress on a more general algorithmic problem called multi-objective submodular maximization, where we improve simultaneously both the approximation guarantee and runtime over previous work in this more general domain. And then finally, we do some experimental analysis and simulation on networks that we gathered from the HIV prevention interventions. So starting out then with how we think about fairness. Actually, I'm going to start first with formalizing a little bit what we mean by the influence maximization problem. So the idea here is that I get as input a graph representing the connections between people in a population. And this graph, in the setting that we're interested in here, will have the nodes associated with a set of groups that represent different demographic groups in the network. And so now I, as the intervention designer, get to choose a set of seed nodes, S, where I have a limited budget of k nodes. And influence will diffuse outwards from those seed nodes S according to what's called the independent cascade model. And so the independent cascade model is in some sense the kind of simplest model for information propagation. The idea is just that every edge is labeled with a propagation probability that describes the likelihood that if one receives information, they'll pass it on to the node on the other side of the edge. And so then given this sort of probabilistic model for how information will diffuse, I can define a function for every group I, which is just the expected number of nodes in that group that will be reached. And so then typically, the objective that we use is a measure of sort of total utility or social welfare, which is just the sum of the number of people that are reached across every group. So the total number of people that are reached. So now, when we think about moving beyond social welfare and defining fairness, this is of course a sort of notoriously difficult task. And here we're going to look at the consequences of two particular definitions of fairness that we could write down. So we're not trying to claim that these are somehow the only ways that you could define fairness. And I'm interested to hear your thoughts about these kind of higher level choices. So the first definition that we look at is maximum fairness. The idea here is that you'd like to maximize the welfare of the least well-off group in the network. And so I can write this down with a maximum optimization problem where the max is over my choice of seed nodes, and then the min is over all groups in the network. And so now my objective function is the minimum fraction of nodes that are influenced within any group. So this is reasonable in the sense that we would like to somehow pay more attention to groups that are getting the least utility from our intervention right now. But it does have a potential drawback, which is that it's sort of agnostic to how well the intervention actually works in different groups. So here's a kind of stylized example where we have two groups, a blue group and a green group, and the blue group is really well connected. So there's somehow a good candidate for a social network intervention. We expect that information dissemination will actually work well in this group. But the green group is really sparsely connected. There's only a couple of edges, and so now you have to select a lot of peer leaders to get anywhere because if you select someone as a peer leader, they don't actually know that many people. They're going to have a very limited impact. And so the maximum definition of fairness is going to force us to spend essentially our entire budget on the green group instead of spending it in the blue group where we get a much higher impact. And at a higher level, this suggests a sort of irrationality about how we're approaching the problem to begin with. That the green group would really be better served by a different intervention entirely because the social network intervention is just somehow not appropriate. So now we also instantiate a second definition of fairness based on cooperative game theory. And so the idea here is that we're going to define how much influence each group should fairly get, and then we'll maximize total welfare subject to each group getting at least that much influence. So of course, making this work depends crucially on what we define a group's fair share to be. And one way of writing this down, which kind of stems from a cooperative game theory idea called the core, is to look at how much influence a group can generate if we just gave them access to a proportional share of the budget. So to make this a little more concrete, here's an example. We have the two groups that I showed you earlier, blue and green. And let's say that the budget is 5 seed nodes. So now, in this thought experiment, we're going to ask what would happen if I gave each group a proportional share of the budget to their size. So if you work out the fraction of nodes that are in each group, that means that the blue group gets a budget of 3, and the green group gets a budget of 2. And now we're going to ask how much influence could each group generate for itself given that budget, and with the particular setting of the probability that influence diffuses across the edges to a border there, then you can sort of work out that the best possible influence for the blue group is 4.25 in expectation, and for the green group it's 2.5. And so now I can add, I'll have associated constraints for each group. I'll say that regardless of what solution I pick, the blue group has to get at least that 4.25 expected influence, and the green group has to get at least 2.5. So they can't be worse off in the combined intervention than they would have been individually if they just got their own share. So writing this down a little formally, I can have an optimization problem where I try to maximize total social welfare. So that's the sum of the objective function, subject to both the budget constraint and also subject to the constraint that every group gets at least their fair share, as I defined it earlier. So that's the constraint that fi of s is at least some threshold t of I. And you'll notice that there's also an additional factor alpha, which we'll think of as an approximation ratio. And this is because the problems that we're interested in solving here are typically on the computational side hard to solve, hard even to approximate arbitrarily well. And so we're going to need to accept some level of approximation of the constraints. So maybe I'll pause here for just a second. It's sort of difficult for me to see if anyone has questions. But if anyone has questions about the way that we've defined fairness here, then you can unmute yourself and go ahead. Okay. Then we'll move on to the next part of the work here, thinking about the price of fairness. And so this is a measure of the total loss in utility, given that you've imposed fairness as a constraint in your optimization problem. So we want to ask more formally, what's the ratio between the best utility that we could have gotten if all that we maximized was total utility, compared to the utility that we're actually going to get, given that we have a fair solution. So this measures somehow the cost of imposing fairness. And unfortunately, you can show that this is pretty terrible in the worst case, that there are families of graphs where the price of fairness is unbounded as the size of the graph increases, and that this happens for either way of instantiating fairness. So this is kind of unfortunate. It tells us that in the worst case, there might actually be a really strong trade-off between fairness and social welfare. But of course, this is for fairly strange worst case graphs, and we'd like to know how bad are things for actual graphs, right? The sorts of social structures that we see in practice. And to answer this question, then we need to tackle the kind of main technical contribution of the work here, which is providing algorithms that can actually solve those optimization problems that I showed you earlier. And then with those in hand, we'll be able to look at the results of social networks. So looking at the algorithm portion of the talk here, I'm going to give you just essentially 2 bullet points of background here. And so influence maximization problems, when I care about total social welfare, are typically solved via a greedy algorithm. And the intuition here is that the objective function has a nice property called submodularity, which just corresponds to diminishing returns. The idea is that every additional seed node that I choose only gives me lower marginal value than the one before it, because many people in the graph will already have been reached. And so you can show that when the objective function has this nice property, that you can just choose seed nodes greedily, and that will give you the best possible approximation to the optimal solution, a 1 - 1 over E approximation. So unfortunately, you can fairly easily show that neither of our problems actually corresponds to an instance of submodular maximization, but the sort of more intricate structure where we take a minimum over groups, or we have constraints for every group, breaks that diminishing returns property. And with it, essentially all of the nice algorithmic work that people have done for influence maximization in general. Fortunately, though, you can show that our problems belong to a more general class of problems called multi-objective submodular maximization. So the general multi-objective problem is that I give you a set of submodular functions, f1 through fm, and then a set of target values, t1 through m, for each of those functions. And now I'd like you to find a seed node such that every function achieves at least that target value simultaneously. And so I think it should be fairly intuitive that these map pretty directly onto the problem formulations that I showed you earlier. So for example, in the group rationality case, I can set the constraint ti. So fi here is the utility for group I. Ti is the utility that they should get according to the group rationality constraint. And now, and then I can have a final function that represents total social welfare. And so I'll binary search for the highest social welfare that I can get while still meeting all of the constraints for the individual groups. So this is nice. We have this kind of like higher level algorithmic framework that our problem falls into. But the algorithmic picture for current work is not as desirable as we'd like in some way. So there's some original kind of theoretical work on multi-objective submodular optimization, which gives you the optimal approximation ratio, 1 - 1 over e. But it's not really a practically implementable algorithm. It takes some time at least to invent the 8 or so. And then there's more recent work. So a paper in Europe a couple of years ago by Dwani, who gave a really practically efficient algorithm, or close to it, that runs in just over quadratic time. But it achieves this kind of force approximation ratio, 1 - 1 over e squared. So it's losing something in solution quality. And so here we bridge this gap. We give an algorithm that gives the optimal approximation ratio up to an additive loss of epsilon, and does it in near linear runtime. And this applies to any multi-objective submodular problem. So I'm going to give just a sort of high-level sketch of how the algorithm works here. The idea is that we're going to start by relaxing the discrete problem to a continuous one. We'll solve the continuous problem, and doing that efficiently is kind of the algorithmically interesting part of the solution. And then afterwards, we'll round back to a discrete set of seed nodes, and that rounding process is already fairly well understood. So I'll kind of skip over it. Introducing, though, what the continuous relaxation looks like. The idea is that I'm going to have a set of objective functions, f1 through fm. And so these objectives are, instead of being defined now on the discrete set of nodes that I picked, they're going to be defined on a fractional decision variable that measures the probability that I include any given node in my solution. And so now I can define my continuous relaxation just to be the expected value of a discrete set where I include every node independently with that set with the corresponding probability. So now the algorithm sketch is that I'm going to maintain a feasible continuous solution. And so by feasible, I just mean that the probabilities sum up to at most the budget constraint. And then over a set of iterations, I'm going to pick a good feasible point, v, and I'm going to take a step in the direction of v. And then afterwards, I'll round back a set of probabilities to a discrete set. And so the high-level sketch is pretty simple here. But the difficult part is figuring out what makes for a good direction to move in each iteration and being able to find that point efficiently. So the high-level idea is that we'd like to guarantee that we make sufficient progress in every iteration in some sense. And so, and what I mean by progress in a more concrete way is that we want to guarantee that the inner product between the gradient of the objective for a given group and the direction that I pick is at least my gap from the target for that group. And so this means that if the gap is really big, I have to make a lot of progress for that group as measured by the gradient. And so you can show that if you have this property, that you'll get the approximation ratio that I described. And so our task is now reduced to finding a v that satisfies this promise. And so you'll notice that I can equivalently rewrite this feasibility problem in terms of v as a Maximization optimization problem, where I'm trying to find a v that obeys the budget constraint and then maximizes the minimum value of that ratio between the progress that I make and the promise and the gap from optimality for that group. And so if the value of this maximum problem is at least 1, then I'll have satisfied the promise that I want to. And so one way to do this would be just to solve it as a linear program, because all of the inner terms there are linear indeed. It's an inner product. The downside, though, is that if I just plug this into a linear solver, it'll take on the order of kind of cubic runtime per iteration, which is already far slower than we want. Fortunately, though, we showed that there's a fast stochastic mirror descent algorithm that can solve this optimization problem in ways that are able to exploit more closely the kind of structure of that optimization problem and some fast gradient estimators that we propose for influence maximization. So I'm not going to go into all the details of that, but it allows us to solve that kind of inner iteration really quickly. And once we put that together in the overall picture, we get the approximation guarantee that we wanted, with a runtime that's has a lot of terms to write out, but if you summarize the final dependence on n, it delivers this near linear runtime that I promised you. So this is nice. We have an algorithm that we can use to instantiate these measures of fairness. And so now I'm going to show just a couple experimental results on real HIV prevention networks. And so here, we took 4 networks from the HIV prevention interventions with about 70 nodes each, and we looked at fairness with respect to the reported kind of demographic attributes of the nodes, their ethnicity, gender, sexual orientation, birth sex, and so on. And we compared the disparity algorithm to both of the fairness concepts that I showed you earlier. Here's the key results. So each of these plots is about one of the definitions of fairness. So the left one is showing the average violation of the group rationality constraints. The right-hand one is showing the minimum fraction of nodes reached across all groups. And then we're looking at what happens if you use either the standard greedy algorithm in blue, if you optimize for group rationality in orange, and if you optimize for maximum value in green. And we find that the greedy algorithm does indeed sometimes neglect smaller groups in the population. So the blue bar is not as good as the other algorithms. But it is possible to reduce this discrepancy. In particular, the group rationality algorithm both reduces violations of group rationality and also has a fairly high minimum fraction of nodes influenced. And we find that this doesn't come at too bad a cost empirically. So the price of fairness is around 1.1. So we're losing on the order of 10% of the possible influence that we could have gotten in total, which is not too terrible. So the kind of takeaways from this piece of work, I think, is that influence maximization can sometimes underallocate resources to smaller groups in the population, but that fixing this is both very achievable computationally and comes at a reasonable cost to overall efficiency. And so we hope that this work will be sort of the first step towards fairer interventions in a wide range of things. So I can pause here. If anyone has questions about this portion of the talk.
Hello.
Hi.
So I have a question about so the first slide, I think, of the second section of your talk, when you compared the optimal fairness with the fair network, I think. So I wanted to see how your
So is it one of these slides here?
I think go further back. Yeah. So not this one. So there was a formula that you were comparing the optimum with the there wasn't any picture in the slide, I think. Oh, this one.
Oh, okay. Yes.
Okay. So how do you define the S of fair?
So that's the seed set that's chosen if you solve either of the fair optimization problems that I showed you on the last couple slides here.
Okay, so and one more question is that your definition of fairness, does that depend on the way that you're selecting the seeds that are going to spread the, so you mentioned that you allocate budget into each group, but apart from that, so the way that you're selecting the seed, does that have influence on the result of fairness?
So the way that we instantiate the definition is just that it's the optimal amount of influence that group can generate given that amount of the budget, which is, of course, not dependent on any particular algorithm. It's just the actual value of that optimization problem. But then in practice, to actually find that value, we need to solve the associated optimization problem. And that's also NP hard to do. So we're going to get an approximation to it.
Okay. So you didn't compare it with when you just do a bunch of experiments on different nodes and running the independent cascade and see how the real results look like. So you didn't do that, right?
So the experimental results do simulate the independent cascade model, yes. So the couple of charts at the end. So
for that experiments, so you selected the nodes based on the your optimization. That one selects which nodes to choose as seeds, right?
Yes.
Okay. Thank you. Thanks.
Any other questions?
I guess if there is no other question, is there any other question?